Hello and welcome to this tutorial on reinforced concrete. In this tutorial, we'll be looking at solving a flanged beam. So we'll be taking all the theory that we've previously discussed, along with everything that we've deciphered from the Eurocode, and we'll be putting it into practice. At the beginning, since this is the first tutorial on flanged beams, I'll do a quick recap before we dive straight into solving an example. So before starting the tutorial on flanged beams, we'll just go through a quick recap. The full theory is covered in the lectures. As we discussed, when the slab and beam are cast monolithically, the slab acts as the beam's flange, and that means that the edge beams behave as L beams and the internal beams behave as T beams, as shown on this slide. The slab doesn't act as a flange across its entire width. Instead, the effective flange width depends on geometry, loading, and transverse reinforcement. The key parameter is the distance L0 between points of zero moments, and we use the Eurocode limits for end spans, interior spans, and cantilevers when calculating it. It is important to emphasize here that in this picture, we are looking at the beam, and these boundary conditions, or the supports you see, are the columns. It's what the beam is resting on. Looking now at the other direction, the effective flange width comes from adding the effective contributions from each side of the web. Each side width is limited by the Eurocode expression B effective I equals 0.2 Bi plus 0.1 L0, but it can't exceed 0.2 L0 or the actual slab width on that side. Adding the two sides plus the web gives us the total effective flange width. This recap example just shows how we calculate the effective flange width step by step. Here we have a continuous slab monolithically cast on beams placed at 6 meter spacings. The beams are 700 millimeters deep by 500 millimeters wide, and the span of the beams is 8 meters, and the beams themselves are simply supported. So looking first at the beams, L0 is L in a simply supported beam, so we simply have 8 meters or 8,000 millimeters. From then on, we look in the other direction. What is the distance between the beams themselves? Really, that would usually mean how often are the beams spaced. So in this case, the beams are spaced at 6 meters spacing, meaning that center to center, the distance between the beams is 6 meters. B1 and B2 are equal in this case, and they go from the edge of the beam width to the middle of the span. So in this case, 6,000 would give us center to center span, minus the width of the beam, 500, divided by 2, and that will give us B1, which in this case is equal to B2, because the beams are spaced at 6 meters consistently. We then need to look at B effective 1 and B effective 2. In this case, it is 0.2 times Bi, so B1 or B2, which we calculated, plus 0.1 L0. We have all of these, and we can find that that works out as 1,350 millimeters. We need to check that that is smaller than 0.2 L0, which it is in this case, and therefore we can calculate the full B effective, as you can see in this drawing, as BW, so the width of the web, plus B effective 1 and B effective 2, which in this case are the same at 1,350. That in total gives us a B effective of 3,200 millimeters. So that essentially is the effective width of the flange. This is a quick recap of what happens when the neutral axis lies fully within the flange. If lambda x is equal or smaller than hf, so the height of the flange, it means that the concrete below the flange has cracked and is no longer able to contribute to compression. In that case, the beam behaves like a rectangular section with an effective width of B effective, like we just calculated, and an effective depth of D. The limiting case occurs when the neutral axis just reaches the bottom of the flange and lambda x equals hf. At that point, the maximum moment that the flange alone can resist is given on this slide as eta times FCD times the effective width, B effective, times HF, the height of the flange, times D minus HF over 2. This represents a rectangular stress block of width, B effective, acting over the flange depth, HF. So if the design moment is less than or equal to this value, the beam can be treated as a singly reinforced rectangular section using B effective on an effective depth, D. The T-shape only becomes relevant once the neutral axis drops below the flange. On this slide, we can see what happens once the neutral axis drops below the flange and the stress block spreads into the web. In this case, the compression is shared between two regions. The flange shown here in blue, carries a compression force based on its effective overhang. So its contribution is C1 eta times FCD, and then open brackets B effective minus B web times HF, the height of the flange. Below that, the web contributes an additional compression force, C2, and that equals eta times FCD times BW times lambda x. And that comes from the rectangular stress block acting over the depth lambda x minus HF. And that comes from the rectangular stress block acting over the depth lambda x. Because the compression is split between the flange and the web, there are two different lever arms to consider relative to the tension steel. The flange compression acts at a lever arm of Z1, which is equal to D minus HF over 2, while the web compression acts at Z2, which is D minus lambda x over 2. Both contributions must be accounted for when evaluating the total moment resistance. This slide brings the flange and the web case together by taking moments around the tension steel. Each compression component contributes its own moment. The flange compression C1 acts with the lever arm Z1, and the web compression C2 acts with Z2. Adding these gives a total moment of C1 times Z1 plus C2 times Z2. From equilibrium, the total compression must balance the tension in the reinforcement. So T, the tension in the reinforcement, which is AS, the area of reinforcement, times Fs, the strength of steel, has to equal C1 plus C2. If the area of steel is large enough for the yielding to occur, the steel stress is taken Fs as 0.87 Fyk. Substituting these relationships and simplifying gives the expression for the maximum moment resistance of a flange section without the need for compression reinforcement. The final form separates the flange contribution and the web contribution, normalize by B effective times D squared times FCD, and uses the limiting neutral axis depth XU consistent with the Eurocode strain limits. The final step applies when the design moment is larger than the flange-only capacity M flange, but still below the maximum moment M max. In that range, the neutral axis lies somewhere within the web, so we solve for x using the full flanged beam moment equation. The left-hand side is the applied moment normalized by B effective times D squared times FCD, and the right hand combines the flange contribution and the web contribution, each expressed in terms of x. The value of x must not exceed the ultimate neutral axis depth xu from the Eurocode strain limits. Once x is found, the required reinforcement follows directly from equilibrium. The tension force, AS, times 0.87 Fyk, must balance the sum of the flange and web compression forces, C1 and C2. This gives the steel area needed for the section to resist the applied moment. In this flowchart, I've summarized the full flanged beam design process. We start by calculating the design moment M that includes self-weight and determining the effective flange width BF, or B effective. The first check is whether the entire flange can carry the compression block. That gives us M flange. If the applied moment is less than this value, the beam behaves like a rectangular section with a width of B effective and a depth of D, and the design is straightforward, just like we've done before. If the moment, however, exceeds M flange, the neutral axis has dropped into the web, so we need to move to the next limit state, the maximum moment the section can resist without compression reinforcement, M max. This expression accounts for both the flange and the web compression zones using the limit neutral axis depth XU. We then compare the applied moment to M max. If M, the moment, still falls below this upper limit, we solve the moment equation for the actual neutral axis depth X, ensuring it does not exceed XU. The required reinforcement then comes directly from equilibrium. The tension force, AS times 0.87 Fyk, must balance the sum of the flange and web compression forces. If the design moment exceeds M max, the section cannot be balanced by tension steel alone, and we need to either add compression reinforcement or to revise the section. So now that we've been through all the theory, let's get stuck into an example. This example brings the full flanged beam procedure together in a practical design scenario. Here we have an 8-meter simply supported T-beam carrying a 100mm slab, which is spaced at 3-meter centers. The key section dimensions are a 350mm overall depth and a 250mm web. The loads include both permanent actions, which are self-weight plus finishes, and a variable load. With the material strengths and reinforcement details given, the aim is to calculate the required area of tension steel. So, in practice, what does this structure actually look like? Let's have a look at a rough sketch. So we can see here a slab sitting on beams. The beams are spaced at 3 meters center to center, and the beams themselves sit on these two columns at either end, making this simply supported, and that is 8 meters. So that gives us a perspective of what we look for when we try to determine L0, which is the direction of the 8 meters, and what we look for when we try to determine the B effective, which is looking from the side of the 3 meters. So designing that T shape. Obviously, we don't want to design the first beam because if we design the first beam, we only get half of the effective flange. So we will design one of those internal beams that you can see here. So perhaps the second or third. We start off using calculation sheets, and in them we write on the very left-hand side the reference that we're referencing. In the middle, we have our calculations, and in the output, we put anything that we're carrying forward. I've started off by just putting the input. We know that the length of the beam is 8 meters, the width of the web is 250 millimeters, the height of the beam is 350 millimeters, and the height of the slab is 100 millimeters. We also have some information on the cover, which is 30 millimeters, on the main reinforcement diameter, which is 25, and on the secondary steel, which is 8 millimeters. FCK, the strength of concrete, is 25 megapascals, and the strength of steel is 500 megapascals. We've also been given the permanent area load in kilonewton per meter square and the permanent variable load, 4.5, also kilonewton to meter square. The first thing we want to do is design the load and the ultimate moment. Now, since these beams are spaced at 3 meters center to center, the loads on the beams are 3 times 8 for the permanent load, and multiplying by the 3 will give us a uniformly distributed load of 24 kilonewtons per meter. And similarly for the variable load, we have 3, the spacing between the beams or the frames, times 4.5, which gives us 13.5 kilonewtons per meter. The design load, therefore, is the safety factor of 1.35 for permanent load times the permanent load, and 1.5 for variable load times the variable load. These are the safety factors from the Eurocode. And this gives us a design load of 52.65 kilonewton per meter. Since this is a simply supported beam, it's pretty easy to calculate the maximum bending moment, which will occur obviously at mid-span, and it'll be WL squared over 8, which in our case is going to be 52.65 times 8 square, which is a span, over 8. And that gives us a moment of 421.2 kilonewton meters. And now that we know the loads in the moment, we can move on to calculating the effective flange. I've left the little diagram from the Eurocodes up here so we can see exactly what we're calculating. We start off by finding B1, which in this case is equal to B2 because everything is spaced at 3 meters distance. And so what we're looking for really is from the end of the width of the web to the middle of the span. If the full span from center to center is 3,000 millimeters, 3 meters in millimeters, minus 250, which is the width of the web, and divided by 2 to give us half of that distance. And so we find out that B1 equals B2 equals 1,375 millimeters. In a simply supported beam, looking at the supports of the beam itself, with a span of 8 meters, we get that L0 is 1 times L, in our case, 8,000 millimeters. We can now find what B effective 1 and B effective 2 are. They are 0.2 times B1 or B2 plus 0.1 L0. In our case, that is 0.2 times 1,375 millimeters, which we just found, plus 0.1 times 8,000. And that gives us 1,075 millimeters. Now this needs to be smaller than 0.2 L0, which is 0.2 times 8,000 in our case, which works out as 1,600 millimeters. We also need to check that the B effective is smaller or equal to BI, so B1 and B2, because obviously you can't pass half of the span because you'll encroach on the next beam's effective flange. And as we can see here, what we calculated, 1,075, is indeed smaller than B1 and B2, which are 1,375. And the last thing we need to do is calculate the full effective flange, which is the width of the web plus the width of each effective flange from each side. So B effective 1 and B effective 2, which in this case are equal. So it works out as 2 times 1,075 plus 250, and that is 2,400 millimeters. And that needs to be smaller than the whole distance between midspan to midspan, which is B, and in our case is 3 meters or 3,000 millimeters. What we want to do now is check if the flange can carry the entire moment or if the stress block needs to extend into the web. So first thing, we need to find D, the effective depth. And that is 350, that's the total height of our beam, minus 30, which is the cover, minus 8, which is the secondary steel or the shear steel, and minus half of the principal reinforcement. And that gives us a D of 300 millimeters. Now that we have D, we can calculate the moment that the flange can carry without extending into the web. So you have eta, which is 1, times FCD, which is the strength of concrete divided by the safety factor of 1.5, times the effective flange, which we just found, which is 2,400, times the height of the flange, or the height of the slab, which is 100, and that gets timed by D, the effective depth, minus HF over 2, which is 100 over 2, and I'm multiplying here by 10 to the minus 6 to organise my units, because FCD is in megapascals, which is newtons over millimetre square. I've got here other things in millimetres, and I want to end up with a moment that is in kilonewton meters because it'll be easier to compare to the moments that I already have. And if we work it out, the moment that the flange can carry is 998 kilonewton meters. What we need to do now is check if the design moment, the moment from the loads that we're applying on the structure, is smaller or equal to the moment in the flange. If it's smaller, that means that the flange can carry the whole moment. If it isn't, it means that we need to take advantage of the web. In this case, the moment that we have is 421.2 kilonewton meters, which is definitely smaller than the moment that the flange can carry, which is 998 kilonewton meters. So that means that the flange can carry 998, but we only need to carry in this whole design 421.2. So definitely the flange is able to carry all the moment. And in this case, we can then design the beam as a rectangular beam of B effective on D, or 2,400 millimeters on 300 millimeters. And now we can finally calculate the area of reinforcement as a rectangular beam. So first we calculate K. This is exactly the same as in a singly reinforced beam, only here we've got B effective instead of the width of the beam or the width of the web. So in our case, we've got a moment of 421.2, and we need to divide it by the effective width of the flange, which is 2,400, times D squared, which is 300 squared, and times FCK, which is 25. Once again, just to organise the units, because here I've now got kilonewton meters for the moment, and at the bottom I've got megapascals and millimeters, I need to multiply by 10 to the power of 6. And if I do that, I find out that K is 0.0782. Once I have K, I can calculate Z. We can see here the equation for Z. All we need to do is substitute D, which is the effective depth of 300, and the K that we've just calculated. And we find that Z is 277 millimeters. We do need to do a check, however. We need to check that Z is under or equal to 0.95D. 0.95D in this case works as 285, and therefore Z is 277 millimeters. We can take that forward. Now, if 0.95D was smaller, we would take that smaller value. So if it was, say, 270, we would take the 0.95D as 270. And the last thing we can do is find the area of steel required, which is the moment divided by 0.87 times FYK times Z. And now we have everything. So 421.2, that's the moment, divided by 0.87 times 500, that is 0.87 times FYK, and times the Z that we've just found to be 277. That gives us a required area of steel of 3,494 millimeters square. What we can do now is find out how many bars of 25 millimeters get into that area, but the main thing is we have found how much reinforcement is required for this flanged beam where the stress block does not extend into the web. And that is how we solve a flanged beam when all the compression stress is in the flange. Join me next time where we discover what happens when the stress block continues into the web.